Hello everyone. In today's video, we will be solving the 1D heat equation. So the 1D heat equation, what is it? Well, if you've taken a partial differential equations introduction class, you would already know what this is alongside the wave equation, Laplace equation, Poisson, and etc. But if you haven't, well, this is a nice little introduction, but a little bit of self-study if you don't know much about partial derivatives or about the course in general. So we are gonna be solving this right here. We have our the image on the right, but we want to talk about what's on the left side. So left side is the 1D heat equation. It's homogeneous. It is parabolic. And what we have is we have u sub t is equal alpha squared times u sub xx. And if we translate it into partial derivative notation or in Newton's notation, we get we get this right here. This is our heat equation in Newton's notation. And we have is del u del t is equal to alpha squared times del squared u over del x squared. The both top and bottom equations are exactly the same. The notation is different. It's all up to a person, a mathematician, which they prefer and which is more easier to read. And how we characterize this is, well, our left side equation del u del t is our time profile. It's our time evolution of the curvature on the right, and our curvature is the temperature profile of, based on the general solution, how our temperature curves in the space, curves in 1D, 2D, 3D, in n dimensions. And now we have alpha squared. Well, alpha squared is a thermal diffusivity, which means that it basically tells us how fast a material absorbs, or how fast heat absorbs into a material. So we have low alpha squared, it means our heat will absorb quickly into material. For larger a, or I'm sorry, larger alpha would mean that it will take some time, longer period of time over our time profile in the curvature for the temperature to evolve. And our general solution will describe that with a graph, of course, and what that shows. So first, we want to basically generalize a real picture of what we're looking for. So we have this 1D rod on our right, this image with length equal to 2, and we have our endpoints right here, this left and this right. And what we'd have is that we have our initial conditions, u, a position at 0 with time is equal to 0. And then on both sides, so x equal to 2, we have u, oops, we have u 2t is equal to 0. So we have homogeneous boundaries, meaning that our endpoints from the beginning and end endpoints, they are basically the same. So this makes it easier to solve for our general solution. And of course, we can say that alpha squared is equal to 1. This gives more simplicity in our general solution. Just a simple general solution for solving this 1D equation. So if we're solving this, we must introduce separation of variables. And separation of variables is a nice technique in solving for these partial differential equations. Solving the heat equation, the wave equation, most likely the Laplace equation. We don't. We do integration on both sides. It's another tricky method. And then of course there's more methods such as Green's function, which is much harder than this. And so what we would like to do is introduce this. So we want to make this partial differential equation convert into an ordinary differential equation. How we do that? Well, we let u equal to our temporal function, which is our time profile. So we have big T, lower t, multiplying by our spatial function, which is our curvature that we see. So big X, little x. So this just tells us this is our temporal function. Right here, this is our temporal function. And then right here, this is our spatial function. And we need to solve that. We need to separate them and solve for individual functions of them, and we combine them together to find our general solution. So this right here, if you know what t of t is and x of x, multiplying together, that is our general solution. So what we like to do is we have u sub t is equal to, well, that's just t prime of t times x of x. And then u sub xx is equal to t of t x double prime of x. So now we just plug them into the original partial differential equation for our heat equation. So we have t prime of t x of x is equal to alpha squared t of t x double prime of x. So now we want to get rid of them. We want to separate them into different things. We don't want t and x to be on the same side. We need them separate. So what we do is we divide by t of t x of x divide this by t of t x of x. So what we get is the x of x goes away, and our t of t goes away. So now we are left with t prime of t. Of course, we divide alpha squared into the other side, so we have alpha squared t of t is equal x prime of x over x of x. So this is our, now it's an ODE. So yes, now we convert into an ODE, and now we can just solve them individually. Our temporal function. Oh, actually, this is also another thing. We equal to negative lambda. So negative lambda is our separation constant, and the reason for this is so that when we have our temporal and spatial functions, we want to separate them, multiply them with each other. Basically, move our equations or variables into one whole side, making it a simple ODE, either first or second order, and we solve for the eigenvalues of those equations to get a general solution for that ODE. And we'll show that here. So we're going to solve for temporal, our time function. And so our temporal function, we have t prime of t plus lambda alpha squared t of t is equal to 0. So this is a 1D, this is a, not 1D, but a first order linear ordinary differential equation. Because we have, it's linear because we go from the first, our equation, original equation right here, and we go to our prime right here. So the solid, we can do the integrating factor method, which can be simplified. So t of t, if you take in the ordinary differential equation, you have to memorize this. This is just equal to 1 over mu of t times the integral of mu of t. I call this big G of t, which is the 0 right here, dt plus, we'll call it C naught. And G of t is equal to 0. And mu of t, we first should define mu of t. This will be equal to e to the power of the integral of f of t, or I like to call it h of t, dt, and h of t is this right here. So I kind of just skipped ahead without explaining because this is a concept you will learn in a ordinary differential equations class in college, and this is what we get. Our temporal function is c naught e to the power of negative alpha squared lambda of t, and we can describe this as being a decaying exponential function. So our spatial function, well, we want to define this as x prime of x plus lambda x of x is equal to 0. So this is a second order ODE. And of course, solving this is pretty easy. We have a equal to 1, b equal to 0, c equal to lambda. And we put this using the quadratic formula. We will get that, of course, we call it e, which is the eigenvalues, is equal to plus or minus the square root. Well, b squared is 0, so we have negative 4 lambda over 2. And simplifying this, we get, what we know is that x of x is equal to a sine x square root of lambda plus b cosine of x square root of lambda. Okay, well, if you take an ODE class, you know where we get this because it's in e to the power of alpha x. The only issue is that alpha is equal to 0 in this, so our exponentials go away. So now what we do? Well, we need to apply initial conditions. So we need to apply x equal to 0 first. So that will get us that x of 0 is equal to 0. So we have 0 and sine, so we can just look at this. Sine of 0 is 0, so this a goes away, and cosine of 0 is just 1. So 0 equal to b. So our general solution, or final solution for the spatial function, will not include the coefficient b. It's plus or minus I root lambda. Well, this is just b. And if we know what a, if we have a complex eigenvalue, so now we have like x equal to 2, which means that we have x of 2 is equal to 0. So what we'll have is 0 is equal to, well, we know b is not there, but we know that sine of 2 times square root of lambda, it won't be 0. So we have a sine of 2 to the square root of lambda. So what do we do? Well, what values will just make sine equal to 0? And well, we know that it's equal to n pi. So every n pi, n is in natural numbers, positive natural numbers from 1, 2, 3, 4, 5. We know that 0, if we look at a unit circle, pi, sine of pi is 0, sine of 2 pi is equal to 0, sine of 3 pi is equal to 0. So you want to equal to this n pi. You want to look at these coefficients in here. So 2 square root of lambda is equal to n pi. We want to solve for lambda, so divided by 2. Square root of lambda is equal to n pi over 2, which will mean that lambda is equal to n times pi over 2 squared. So now we solve for lambda, and that also makes it easier if you plug in lambda back to our temporal function. And we know a is just our constant, but it goes away after we divide by a. So this means that x of x is equal to sine, and so we just get pi n x over 2. This is our spatial function. So now we can plug it back in. We know what x of x is, and we know what t of t is. So that means u x of t, our spatial and temporal, or our position in time, is equal to c naught e negative alpha squared pi n over 2 squared t times sine of pi n x over 2. And we know that we don't want n values equate to this, so we can introduce an infinite series showing that we combine all the terms from n equal to 1, n equal to infinity. So u x of t is equal to the infinite series from n equal to 1 to infinity, c naught e negative alpha squared pi n over 2 t sine of pi n x over 2. So we're not done yet. And because we have this c naught coefficient right here, we have this c naught right here. And how do we get rid of that? Well, we also introduced the initial condition. And to minus the initial condition, u x at t equals 0 is equal to x, 1 minus x. So, well, what do? We plug back into here, u x of 0 is equal to our infinite series from n equal to 1 to infinity. Well, e to the power of t, which is equal to 0, just the exponential goes away. So left with c naught times sine of pi n x over 2. And this looks similar to solving a Fourier coefficient of a Fourier series when we're trying to find the approximation of a periodic function. Well, sine will be equating to b sub n. So what we can do, well, this is also just equal to x, 1 minus x. And then the formula for solving for c sub n. So c sub n is just equal to, since it's periodic, well, we can say it's periodic. So we just say 2 over L times the integral from 0 to L of f of x0 sine of pi n x over L. Oh, well, we know L is equal to 2, so we can just place all the 2 here. Of course, we multiply by dx. 2 over 2 is just 1. So this is just the integral from 0 to 2. And we know that f of x, these two are basically the same. From 0 to 2, x, 1 minus x, sine pi n x over 2 dx. This is what c naught would equal to. And this is, well, we can't really integrate this really nicely, but we can use integration by parts. We will not just do the hard method of uv minus the integral of v du. We're just using the tabular method for solving this. So after doing some mental math on solving for c sub n, how to change the coefficients we're looking for n, we find that c sub n is equal to 4 over pi n times negative 1 to the power of n plus 16 over pi cubed times n cubed times 1 minus negative 1 to the power of n. So we found just c sub n, but we want to look at c sub n in different conditions, of course. So we're going to do if, so we're going to have if n even, then c sub n. Well, if we see that 1, we can look at this right term. If negative 1 to the power of 2, it just gives us 1. So 1 minus 1 is 0. Negative 1 to the power 2 is just 1, so we're just left with 4 over pi n. And so for n odd, so 1, 3, 5, 7, if we do n equal to 1, we get c sub n is equal, well, negative 1 to the power 1 is just negative 1, so we get negative 4 over pi n. And for this term up here, same thing. Negative 1 to the power 1 is negative 1. 1 minus negative 1 is 1 plus 1, which is equal to 2. So we just get, and 16 times 2 is 32. So we get plus 32 over pi cubed n cubed. So this is piece, we can put this in piecewise. And for any other n, well, we can just say it's equal to 0, which isn't the case. It's even and odd. We'll combine all positive integers, of course. So now we can put this into our general solution. So this is the general solution of our 1D heat equation as we saw above. We have the infinite series of all n terms from 1 to infinity of c sub n on the left times our decaying exponential of time times our sine of pi of x over 2. And I will show you what this general solution looks like in Desmos. So this is what our general solution looks like in Desmos. Of course, infinite series goes on. We want to approximate this. So as you can see, this looks like normal sinusoid, but as we increase with n, it looks discrete. Well, it's also because this is a Fourier series too. The general solutions of most PDEs are Fourier series. And if we look at the initial condition, it matches up. It from 0 to 2, it matches up. It basically approximates the curve. Of course, here is a error approximation. This is a fundamental thing to learn in Fourier analysis class. So we want to look at the time of evolution. T equal to 0, we can see it's the same as our initial condition, x times 1 minus x. As time evolves, we can see that it diffuses. It diffuses towards equilibrium, goes towards 0. As we go back the other way, it goes back to the initial condition. Well, we can slowly look at this and see that it quickly diffuses around this point and this point, where the maximum and minimums of our general solution. As we can see, they quickly diffuse and go from 0 to 2. After t equal to 1, it will be at 0, and that means over the span of basically, you can do 1 minute, 1 hour, 1 day, the heat of this 1D rod diffuses into the rod. It will go from wherever our original condition was to 0. So that is how we solve a 1D heat equation. And maybe more videos come like this, solving the wave equation, maybe solving another 1D heat equation in 2D, 3D, or just some simple other math videos. So thank you.